Can I just do an audio check? Should have audio coming through now. If someone can let me know if you can hear that, and if you can hear it loudly enough, that'd be great. Excellent. Thanks very much. I'll just mute my mic and I'll be back at 9 o'clock and we'll get underway with the lecture. Thank you. I make it 9 o'clock, so let's kick off with the lecture, shall we? Before we get underway with the lecture, I'm going to just say a few words about this week's Assess Lab. You'll be aware that in week 4, we've just started week 4, there's an assessed lab. This contributes 5% towards your overall course grade, and it means that for the overwhelming majority of you, you turn up to your scheduled face-to-face lab, and you complete a programming activity that should take you no more than an hour. There's a 2-hour session, so we've got enough time for people to turn up from whatever commitments they've previously got and get in the room and get underway. It'll start 10 minutes after the hour. You've got up to an hour to complete the programming exercises. There are 2. We discussed the style and sample content in last Thursday's lecture. And if you watched that lecture, I gave you a place where you could find a sample paper, and I've seen on Discord over the weekend that a number of you have been working through those sample paper. So I said for the overwhelming majority of you, you turn up to your assessed lab this week, and in your 2-hour assessed lab and 2-hour lab session, face-to-face lab, and then complete an assessed lab sheet. There'll be small variations in the questions that are asked through the week, but everyone will get comparable difficulty questions, and they'll be similar to the sample paper that was posted and discussed on last Thursday. I said for the overwhelming majority of you, because some of you, a small number of students that are located overseas, are completing this course online, in which case you'll complete your assessed labs via Zoom. So what that means is that for the Callaghan-based students, we won't run Zoom labs this week. The only Zoom labs that'll run are ones that'll be supporting the online students, and I've separately been in contact with those students to let them know the arrangements for completing their assessed lab via Zoom. So if you're here in Newcastle, enrolled in the Callaghan and attending the Callaghan campus, then this week, week 4, there'll be no Zoom labs. I'll put an announcement out on Blackboard and follow that up on Discord, but just to let you know, give you a heads up now, that'll be the case for this week, and we'll resume Zoom labs next week. Week 4 is an important one because we've got this assessed lab running. One of the reasons we run an assessed lab relatively early in the course, we've only had 3 weeks of content. One of the reasons we do that is because we want students in this class to have had the opportunity to test their understanding in advance of the HECS census deadline, which is Friday, the 19th of March, this Friday. So this Friday is a really critical day for students in this course, and in fact for all courses. If you withdraw from this course, up to and including some time on Friday, then there's no HECS implications for you. The course never exists on your transcript. It's as if you never were enrolled. If you're enrolled past Friday, that's not the case. There are HECS liabilities for you, and as far as the university is concerned, you're enrolled in the course, and therefore you're either on track to get a fail, a withdrawal, or a pass, or a credit, or a distinction, or a high distinction. You're in the course after this Friday, and so we really like to give students the opportunity to test their understanding in advance of that HECS census deadline. So that's one of the reasons we assess students relatively early in the piece. But we've certainly covered some interesting content so far, some interesting and some powerful content, and I want to continue with the delivery of that content now. Although I'm making a deliberate effort this week, week 4, to keep the rate of new content to a minimum. So we will see some new content in this morning's lecture, but there'll also be a little bit of revision again, and also some more general comments about debugging programs. So the lecture overview for this morning, it wouldn't surprise me if we finish this in about 90 minutes rather than the full 2-hour slot. We're going to look again, take one last look at comparing the two iterative structures that Python provides for as part of the Python language. We looked at for and while loops last week, and we're going to look at them. We looked at them last Monday. We looked at them again on Thursday, and I'm going to take one final look at them today. And that really underscores their importance as powerful programming tools. As so often the case in life, things that have great power are often take a little while to get your head around. And I think that's probably the case for for and while loops. So I'll say a few words about them. I also want to take a pause and look at in the second part of today's lecture. I want to take give you some more high level advice on debugging programs, making programs run as you want them to, removing the errors in them. I've noticed some really interesting discussion happening in the Discord channels around debugging, and I want to give you some strategies that I've found useful over the years for debugging programs. It's actually quite difficult to encapsulate what I do and what programmers do when they debug, but I've got some high-level comments that are also very practical, that help you develop not just get answers for questions, but develop strategies. And the third thing I want to discuss with you today is some new content, and it's generating random numbers in Python. We looked at an example last week sometime where we used the example of rolling a dice, and the number 1, 2, 3, 4, 5, or 6 could come up, and we just hard coded the number that it was rolled in the dice into the program code. It's often really handy to be able to generate random numbers, and Python, like all programming languages, provides that ability, and I want to get you started on that process today. We might look at some other ways of generating random numbers later in the course, but what you see today will get you started, and is really very handy, very powerful. So let's get underway with the course content, the lecture content proper. Last week we introduced for and while loops as ways of getting Python to do something that up until that point we'd not been able to do, which is to get the same line of code executed multiple times over. So to iterate in a program. Now, the simplest iterative task I can imagine is being able to just print a sequence of numbers. So let's choose a count sequence from 1 to 10 and write some code to do that. The two iterative structures that Python provides are for and while, and I've given you sample code on slide 3 here to generate and print the numbers 1 to 10. And you'll see on the left, we've got a statement that says for I in range 1, 11, 1. A reminder at the bottom of the page that the range 1, 11, 1 actually generates a list of numbers from 1 to 10. So the way that I've begun to read statements like range 1, 11, so the numbers here 1, 11, 1, the significance of them is 1 is where we start, the start index. The middle number is the index, so we finish before the index gets to 11. So in this case, it's 1, and we increment by 1. So we start at 1, and we increment by 1. So we increment from 1 to 2 to 3 to 4, and we stop before we get to 11. So in other words, the statement range 1, 11, 1, in fact, generates a list of numbers through 1 to 10. I could have typed them out, but I wanted to use the more compact form on the left. So that's a force, and we'll run this live in a moment. The Python program on the right also generates the list of numbers 1 to 10. And you can see one obvious difference between the code on the left and the code on the right is that while the for statement takes just 2 lines, the while loop takes 4 lines. Why is that the case? Because inside the body, the indented body of the for loop, we've got a print statement that prints the index. On the right-hand side, we've also got a print statement. We've got an additional statement. So let's look at the lines one by one on the right-hand side and see what's going on. The very first line on the right-hand side in the while loop is an initialization of the loop index I. So I is equal to 1. And then we have a statement that says while I is less than or equal to 10, do some stuff. And the stuff is print the value and then a second statement. So you'll see that on the right-hand side, the loop index needs to be explicitly initialized. Whereas in the for loop, it's built into the statement of the for. For I is in the range 1 through to 10. We don't have to explicitly initialize it with the for loop, but we do have to explicitly initialize it with the while loop. So then in the while loop, we print the number. So the first iteration through this loop, we print the number 1 because it's the index and we've initialized the index to be 1. And then the second statement in the while loop, we update I by incrementing it by 1. We take it to the next element of the count sequence. I is equal to I plus 1. In other words, I is assigned the value of I plus 1. So the first pass through, we print the value 1. We then increment the index from 1 by 1 to give it the value 2. The index has then got 2, and we go back to the top of the while loop and check the condition, check the logical condition. Is I less than or equal to 10? Well, it's just been incremented to 2. So yes, it is. Next iteration, we print the number 2, we increment it to 3. Is it less than or equal to 10? And so on. Which is really interesting. What it means is that there are real key differences between the for loop and the while loop. So in the while loop, the counter needs to be explicitly initialized and also explicitly incremented in the loop body, whereas the for loop does these 2 tasks automatically for us. So you might think that, the simpler, the shorter code on the left is to be preferred. It would be for this simple task. If you ask me to write a loop of my choice to display the numbers 1 to 10 on the console, I would choose the for loop on the left in this case. For more complicated programming tasks, I wouldn't necessarily choose a for loop. They're both available, and it might often be the case that the while loop is more suitable. It definitely depends on the problem setting, and it's often not obvious which one is the best. One issue with a for loop is that when you start it, it's going to run to completion. The while loop, it'll only run as long as the condition's satisfied. So it might well be that you're able to write a while loop that as soon as it calculates an answer or finds something, then there's no point in continuing the iterations on out to the end of the list. So it's often the case that the while loop is often more efficient. So that's why I say you should have the ability to write both types of code as part of your programming skill set. One is not to be preferred over the other. It depends on the problem. And sometimes it's even more subtle than that, because it's only by taking on the problem that you really understand the implications of what would be the choice, why you would choose for over while or while over for. And so we're going to look at one final example using a problem setup that we began a couple of weeks ago now, where we kicked a soccer ball in the air and we tracked its height. And we've done a couple of things now. The first was to produce a plot which shows the height as a function of time. We did that a couple of weeks ago now. And last week we looked at the time of flight. We kicked a soccer ball with a certain initial vertical velocity, and we calculated the time of flight by estimating the time at which the curve crossed the horizontal axis. And so we've seen this example before. We're going to use it a third time this morning, and we're going to solve the problem of calculating the maximum height of the ball. So in this case, we're going to calculate that its height on the vertical axis and time on the horizontal axis, and we're going to calculate the height when the ball reaches the top of its trajectory. And we're going to solve that using for and while loops. And I'll just to show both those programming strategies in action on a realistic problem. Now, a point was made in the Discord chat this week that when we're computing the time of flight, why don't we just, we've got an equation for this curve, why don't we just compute the time at which the curve intersects the ground, the horizontal axis, or the height y equals 0. And that's true for a case where we've got a very simplistic trajectory of the ball as a function of time. If we'd had a more complicated simulation of the dynamics, maybe we took air resistance into account, for example. So we kicked a soccer ball and there's air resistance that impacts on the ball's trajectory. Maybe if we simulated the air resistance dynamics, it would be much harder to compute the time at which the ball intersected the ground. Another way of thinking about this problem that'll become particularly relevant this morning is that maybe we've got a soccer ball with a sensor on it and we're getting estimates of the height of the soccer ball every millisecond from a sensor located on the ball itself, in which case you wouldn't expect a lovely smooth arc like this. Depending on how accurate the sensor was, you might get variations in the measured sensor height, the measured ball height, which meant that the curve was a bit noisy, in which case calculating the maximum height of the ball would be more of a challenge because it doesn't necessarily follow this smooth arc. Okay, that's context. Let's go back to the particular problem we're solving here now. We've got an expression for the trajectory of the ball as a function, the height of the ball as a function of time. It follows a quadratic equation. We saw that equation week before last, and I'll show it to you again in Python code on the next slide. And the problem is to use for and while loops to find the maximum height. And we're going to use very different strategies for both for and while loop. And that's what I'm trying to convey to you today. Excuse me. So this code here, you've seen most of it before. The top chunk of code you've seen at least a couple of times now, both in week 1 and week 2. We've got a couple of import statements that allow us to use the NumPy numerical processing library. And we import the ability to produce some plots. The first 4 active lines of the code simulate the trajectory or the height of the ball as a function of time. The key lines here are the lines which set up the linearly spaced points in time, and the computation of the array of heights with this expression for y equals v0 times t minus half gt squared. Seen this code before. I won't go into detail. The middle chunk of the code, I'm going to zoom out and show you it too on the next slide. That's where we're going to use a for loop to estimate the maximum height of the ball. We then display the maximum height, and the closing lines, also you've seen before, they're a plot of the trajectory or the height of the ball as a function of time. And Let's just run that code now. I've got a hot link in here, which should hopefully take me to a place which will generate the code for me. Just to show you where that hot link takes me to a place which will give me this code. Again, this GitHub repository. I've already cut and paste this into my Python setup. So here's the code. Import statements, calculation of the vector of heights, the array of heights. We then use a for loop to calculate the maximum height. I'll come back and look at that code in detail shortly. And then we plot the height. So let's run that code now. If we do that, you see a couple of things. You see the plot, the curve of the height of the ball as a function of time. Seen that a couple of times now. Here's the key part, the new part. We've got a message displayed to the console that has computed the maximum height for us based on this vector, this array, sorry, of ball heights here. So now let's take a look at the code in the middle of this program, which uses a for loop in order to compute the maximum height. So on slide 7 here, you can see towards the bottom of the slide, I've got an extract of the 4 lines of Python code that use a for loop in order to compute the maximum height. And then below that, I've got the printout in the grey rectangle, which shows the largest height was achieved was 1.27 meters. And you saw that when I ran the code live. So before we look at the code itself, I want you to think about the overall strategy. There's at least a couple of ways of locating the maximum height of the ball. Keep in mind, we've already computed the array of ball heights as a function of time, the times being separated by 1 millisecond. The heights are stored as the elements of an array, and the array is called Y. So Y is an array, Y0, Y1, Y2, and so on are the ball heights at times separated by 1 millisecond. So Y0 is the initial height. The ball's on the ground. Y1 is the height of the ball after 1 millisecond. Y2 is the height of the ball after 2 milliseconds, and so on. I think we simulated it for 1,000 points, so we'll simulate the first second of the ball's arc. So one strategy, it's not the only one, but it's the one we're going to use here. One strategy for finding the maximum height of the ball is to look at every single height in the array of ball heights and to locate the maximum value. We want to find the value in that array where the ball height is maximum. It starts at 0, it increases for a while, reaches a maximum, and falls again. So if you think about the values in Y, in the array Y, as we move from Y0 to Y1 to Y2, we go up and up and up, and we find progressively higher values of the height, and eventually we come back down. One strategy for finding the maximum height is to initialize the maximum height at the first value, hold that, store that value somewhere, compare that with the next value in the Y array. If that is higher than the value we've stored as the highest, the maximum height to date, Then we update the maximum height to date, and we compare it with the next value, and so on. And so what we do is at any point in time, we've got a hold of the maximum height that's been located in that array so far. So our strategy is that we initialize the height to Y0, and then we work through the remaining indices looking for a value that's higher. And if we find it, we update our new largest value and we move to the next. Now, this third dot point here, when it says work through the remaining indices I equals 2, 3, and so on, that's a typo. It should say work through the remaining indices I equals 1, 2, and so on. 1, 2, 3, 4. Because the largest height was initialized to Y0, and then we compare the heights Y1, Y2, Y3, and so on. And each time we find that our YI is bigger than the largest, it becomes the new largest. So that's our strategy. I'm separating the thinking of the process to the actual code that implements it. So now we've got the strategy in mind. Let's look at the code. We initialized a variable called largest height equal to Y0. That's the start value for our search. It won't stay the largest value for very long because it takes the value 0 and we know the ball goes up. But we've got to initialize it somewhere, and we're going to use a for loop in the range 1 to the length of the vector, incrementing by 1. So this really says we're going to search exhaustively over the set of indices in this array. Length of y here was 1,000, and we use a linspace function to generate an array of time points of length 1,000. So we start at index 1 and we go up to index 1,000. We've actually got 1,001 values to consider, but because we initialize the largest height to be Y0, we don't need to include the index 0 in this list, this set of array indices. So we initialize the largest height to be the initial height of the ball, and then we set up what I would call an exhaustive search, because we're going to search over for I in the range 1 right up to the top of the array. If we find that the array element at index I is larger than our largest height so far, then we update this largest height to be that value. So that's the value I said we store somewhere. We store it in the variable called largest height. And then the for loop takes us back to the next index in the range. So we started with 1, next index will be 2 because we increment by this third parameter in the call to the range function. So we start at 1, index 1, we go to index element 2. If Y2 is larger than the largest height, then the largest height becomes the height at Y2. Increment again if Y3 is larger than the largest height, and so on, and on we go. And so that's how the program works. Eventually what happens is the largest height takes the value at the top of the curve. The array index is incremented, and we find that yi is not greater than the largest height. But that's okay. We've stored the largest height. We've got a hold of it. We've kept a store of it, and the fact that we check array indices after the peak doesn't matter. In fact, we have to do that to exhaustively search through the array to find the largest value. So that's one strategy for solving that problem. It's actually not a bad strategy if in general, but it's a little, you can see it's a little bit inefficient. If we knew that once we'd found the maximum height and the value started to decline, it's a bit wasteful to have to spend so much computer time checking the values after we've found the maximum. Yes, it's wasteful, but we don't actually know we've found the maximum height in general. We do in this case because the curve's smooth and we know that once we've found a value that's less than the peak, we can stop looking. So, but our strategy here was to exhaustively search. In general, for loops are perfect when you want to do an exhaustive search. when you want to check every single element of an array for some condition, a for loop is the way to go. The second strategy, we've sort of touched on it in thinking about the strategy for with the for loop. If we had to use a while loop to find the maximum height, what we could do is we could look at successive pairs of heights. What characterizes the maximum height or the trajectory up to the maximum height is that at successive time points, the second time point is higher than the previous one. So we know if we look at y0 and y1, we know that y0 will be less than y1 if the ball's on its upward trajectory. Likewise, y1 and y2, namely the ball heights at 1 and 2 milliseconds, if y2 is greater than y1, then the ball's still on its path up. If y2's less than y3, the ball's still on its way up. And we keep comparing successive pairs of the ball heights until such time as the ball starts to drop. So the characteristic of when the ball is still on its upward path is that its height at time index I is strictly less than its height at the successive point in time I plus 1. So in other words, the ball's reached its maximum height when yi plus 1 is less than or equal to yi, namely that the ball height at time instant I plus 1 is possibly less than, maybe equal to the height at yi. So it's possible that we would have two successive time instants where the ball's exactly the same height. More than likely, we don't exactly catch that time point, and what happens is the ball starts on its downward trajectory, and the condition that I plus 1 is greater than yi is false. At which point we can report the yi as the maximum height. So in this case, we can use a while loop to find the maximum height using the code shown at the bottom of slide 8 here. You'll notice that in this while loop, just like it was for the while loop when we counted from 1 to 10 at the start of the lecture, we need to initialize the loop index before the loop header, and then we need to increase the loop index inside the loop body. And so this loop body really does nothing more. It does the only statement inside the loop body. So the only indented statement is the increment of the loop index. So this while loop's not working very hard, but it's checking while ever it happens that two successive values, it's the second value is larger than the first. We haven't found the maximum yet. So just increment the loop index and go to the next pair. And keep doing that until such time as this condition, yi plus 1 is greater than yi, is false. At that point, the loop drops through and we've found index I as the index of the maximum height. Now, I know when I worked through this, I personally found the for loop to be the easiest to get my head around. The while loop took a little bit more to get my head around, but even though the code was shorter, you see that you compare the code there, 3 lines versus the 4 lines. This code's more compact, and as a general rule, when things get more compact, they often they can hide complexity, and that I would say that's the case here. These 3 lines of code are deceptively simple. What you really need to be able to do is work through some examples with real numbers and convince yourself that this code is right. Okay. So what that leads us to then is the second major point in today's lecture, which is debugging strategies. But before I look at them in particular, I just want to say a few words and set the scene. When I wrote this code, when I confirmed that the code in the book was worked as claimed, the way that I did it was I ran the code and I looked at the values in the Y array, and I convinced myself that everything was in place because the ball rising was characterized by successive pairs in which the second pair was larger than the second element was larger than the first, and so on. And then I had to really check that this condition here was satisfied when this yi plus 1 greater than yi is characterized as the ball rising. And when it's not true, we've found the maximum and we can process it. This was probably the first case in this course where this code here was an example in lectures that would really require careful verification that the problem solution was actually finding the correct maximum height. What we're finding then, as we move into the second major point of today's lecture, what we're finding is that after 3 weeks of coding, you're beginning to solve problems where you need strategies for finding the problems when they arise. So debugging is another word for eliminating errors, and I've seen it in Discord a number of times over the past week where students are getting stuck trying to get a problem solved so that it either reproduces the numbers that they know are correct or that reproduces the numbers that are given to you as like the target numbers. So I'm going to talk for a few minutes now about debugging strategies, but let me begin by saying it's not a surprise to me that students are getting stuck trying to debug their programs after 3 weeks. It's not a surprise to me because it's at about this time where you've got enough tools in your hands to be able to solve interesting problems. And interesting is my way of saying not necessarily easy problems the first time you see them. It doesn't surprise me you're getting stuck. It doesn't actually worry me that you're getting stuck, because if you're getting stuck, it means that you're thinking hard. If you're not getting stuck at this point, you're probably not trying, or you've seen this coding, this type of coding before. So my first take-home message is don't be worried that you're getting stuck. It's anticipated that you would get stuck. It's not your lack of knowledge. It's just that you haven't yet built up your skills in finding and solving problems when they arise. It's at about this point that most students that haven't seen programming before start to realize that it's one thing to see code given to you. Here's how I solved the problem. Yeah. Okay, the code looks interesting. Yeah, righty. I read the comments. Yeah, I pretty much know how that works. It's at about this point in the course that when you're trying to solve your own problems, you get stuck because you're learning the syntax of a new programming language. You're also getting your head around how to solve problems, and it often happens that you only really understand the problem once you've written a computer program to solve the problem. So at the risk of being a little bit philosophical, one of the reasons that a course like this introductory computer programming course is so important to you as engineers, and I don't care what sort of engineer you are, electrical, civil, mechanical, mechatronics, environmental, surveying, chemical, no matter what sort of engineer, what you need to do is solve problems. And one way of really understanding a problem is to write a computer program to either simulate or analyze the data from an experiment. And so what you're finding is at the same time as you're learning the programming syntax and some of the features of the Python language, you're also understanding problems the like of which you might not have seen before. So I'm not concerned that you're getting stuck, but it's about now that it might be helpful for me to spend a few minutes giving you some tools for getting yourself unstuck. And debugging is an art form. It's something that you get better with practice. It's also something that can be incredibly frustrating when you're just making your first steps towards learning a computer programming language like Python. When you realize that debugging is a new strategy, I would say it's a key part of the programming process. So here on one page is my personal take on strategies for debugging. Every programmer will have different strategies. Every programmer's strategies would overlap with mine. This is not material I've taken from the textbook. This is material that I've developed over time from experience. They're in no particular order, but in some of the discussion on Discord in the last week or so, I've watched students grappling with problems for which one or two or three or all three of these strategies will help. So the first strategy, and probably the most powerful of the three, I said I wasn't going to prioritize them, but they're all important. Probably the first one's the most important, which is when you're running your code, I've called it running code by hand. That means that when I program, and I've gone around to some of the labs and spoken with you, some of you one-on-one, just about the first thing I've said to you is, can I have a piece of paper and a pen? You can do it on your iPad or a tablet if you like, but you definitely want to do it in somewhere other than your head. You want to get this stuff down on paper. What does this stuff mean? It means understanding what you want your code to do. It means not just sort of understanding what you want the code to do, really understanding what you want the code to do. And that just means not just producing the final result that you want, but thinking like a computer, thinking in single, indivisible steps at each line of your code. What is my code doing? Which variables is it updating? Is it updating individual elements of an array, or is it updating the whole array at once? What's the value of the loop counter? What's the value of the array index at the loop counter? You're really thinking at that sort of indivisible element, the smallest possible calculation step with a pen and paper. Now, sometimes that can happen quite quickly. Sometimes you can be scribbling numbers one after the other, drawing boxes representing arrays, updating the elements of those arrays, and it can happen quite quickly. So don't necessarily think that using a pen and paper is slow, or that this iterative process, this systematic process is slow. It can happen quite quickly, but it needs to be done step by step. It's really easy to fool yourself with, yeah, code looks about right. I think those numbers are right. I think the program's operating as I hoped it would. Really easy to do that, especially when you're getting started. It's easy to say, yeah, those numbers look about right. That's probably what I expected. When you're really trying to debug a program and really verify that it's producing correct numbers, rock solid, put your house on them, correct numbers, then you really want to work at the same time as you're writing your code. You want to be working on paper to verify that each step and is right along the way, and that there's no vagueness. Because you've worked out by now, computers don't like vagueness. They do what they're told. I'd have to say, in all the times in all the years I've been programming, I can't really think of a case where the computer really did something that it wasn't told to do. That's what computers do. do what you tell them to. Now, sometimes that debugging process can be really complicated because there are factors beyond your control that you don't know of in advance, and that makes debugging difficult. But with the sort of code that you're writing here, if you work with tiny little problems that I've called toy problems, small problems, and arrays that values you've calculated using the console, for example, it's possible to debug programs. And I guess the take-home message for me in this first dot point is that near enough isn't good enough when you're debugging. The computer's going to act. The computer's going to do exactly what you tell it to do. If it does something unexpected, and the computer's done what you've told it to do, and the result isn't correct, there's only one logical conclusion, and that is you didn't tell it to do what you wanted it to do. You gave it some other instruction. The computers followed that other instruction. So it's a bit of a mindset shift. When you're debugging, while you'd like your code to be correct, you switch your brain to a different mode of thought where you're trying to find an error. It's like you've created something, a small computer program, and now you're trying to find a problem with it. You'd like to think your creations are without errors, but if the results are incorrect, you've got an error and you need to switch your mindset. So it's almost like, it's a bit philosophical, but it helps to develop that mindset. Treat it like a challenge. Treat it like your friend's giving you their code and you're trying to find something wrong with it. Okay, that's the first overall strategy. The second strategy that I found useful is don't guess at the value of a variable. Print it out. If you've got a loop, if you think you know the values of the variables in an array, the elements of an array when you're working in a loop, don't guess them, print them out. Later in the course, depending on how things go, I might show you how to use a more powerful built-in debugging capability that the Python, the PyCharm IDE provides. I may or may not do that. It might be useful to you. To be honest, 99% of the debugging I've done over the years, I've done with simple print statements, where you just print the values out as you go, and you're comparing that with your code by hand. So on Discord, I've seen a bit of chat with students saying, "Yeah, I think this is an array that I'm printing out, but they're actually printing out an array element, one element of the array, and I think it should have this value." Don't guess at the value. You've got the ability to use print statements. Put them in. Just check that it's doing. If you're guessing what a computer program's doing, then you're using part of your brain to make a leap of faith that you should just be getting the program to tell you how it's operating. And the third strategy I've called take baby steps. And this is especially true when you're developing large pieces of code, hundreds, thousands, sometimes tens of thousands of lines long. We won't need to in this course, but still, if you've got a program that runs over 10 lines of code and there's a problem with it, make it a problem that's got 5 lines in it. Comment out stuff until you've got a program that'll at least run. And then when you change one line at a time and rerun your code, if there's still a problem, if there is a problem, you know the problem must have existed in that line that you added. That's a really powerful strategy. You've got a program that's 99 lines long and it runs just fine. It might not produce the right results, but it runs. You add line number 100 and all of a sudden the interpreter is giving you an error. In general, finding an error in a 100-line program is a challenge. But if your program ran when it was 99 lines long and you've added just one line, you know where to look with the problem. It's in the one line that you just added. So that's another really good strategy. And what that often means is that if you've got a program that's, let's say 10 lines long, and it produces an error somewhere. Okay, start commenting stuff out until you've got a program that's shorter that works, and then progressively remove those comments one line at a time, or as few lines as you can. Sometimes it's not possible to do one line at a time. Maybe you've got a for loop and you've got a problem with the for loop and you need 2 or 3 lines at a time to add in order for the for loop to operate. You can't operate a for loop without its header, for example. But you get the point. Baby steps, smallest step you can take, make one change at a time, rerun your code. So I'm really conscious that I've spent 10, maybe 15 minutes just talking in general terms about what I've acquired through some years of programming experience. I don't expect you to memorize this. You won't be assessed on what are Steve's 3 debugging strategies. What I would suggest is a couple of things. One is keep this page handy, use it as a reference. If you take home just a couple of take-home messages from that page, that's great. Point 1. Point 2 is that as we move forward in Discord, I'll increasingly be, and I probably frustrated you already, some of you already, sorry. You ask for, you post something on Discord that says my program's got a problem with it. What's the problem? Generally speaking, I don't say, the problem's with line 10, you need to change X to Y. What I'll do is I want to give you a strategy for finding that problem yourself. Because once you develop your own strategies, you can take that to solving your next problem. Rather than with your next problem, posting on Discord and saying, I've got it, my program doesn't work. What's the problem? And so one final point on this slide is that this way of thinking, running code by hand, don't guess values, taking baby steps, they've been presented here in the context of this course, ENGG1003. But they're actually pretty good strategies for the other courses that you take, and indeed as operating as engineers. They're all strategies that can be applied. They're all about understanding complicated problems, making them simpler by interrogating the data. Do you really understand it? Not guessing values, really, maybe you're trying to control the temperature in a distillation column and you're guessing what the temperature is. Maybe you could measure that temperature. If you knew the temperature, the control of that process would be easier. So these are strategies that extend well beyond just coding strategies. And so again, you'll probably find it a bit frustrating at times if you're asking questions on Discord and wanting answers. Sometimes I won't give answers, and sometimes the teaching team won't give answers. What they'll give you is strategies, because those strategies are really powerful. You will use those strategies for 50 years. If I give you an answer, your problem's solved and you move on to the next problem. If I give you a strategy, you'll be using them in those strategies in 50 years. So a bit philosophical, but something I feel strongly about, and something that's super powerful as you develop your ability to think like an engineer. Wonderful. Third and final topic that I want to cover with you this morning. This is where we introduce some new content. We've been talking, just about an hour, haven't really covered any new content. Some new ideas in debugging, and a new take on an old problem for the first part of the lecture. Some new content. So far, we've written programs that have run in a way that if you ran them today, run them tomorrow, run them in a week, run them in 10 years' time, they'll all produce the same answers, assuming that you can find a Python interpreter in 10 years' time. Guarantee you will. They produce the same answers each time you run the program. And that seems like a fair and reasonable thing to expect a computer program to do. Although sometimes it's necessary to produce random numbers. Random numbers in Python are generated, all computer programming languages have got the ability to produce random numbers. A simple example that we saw last week was where we talked about winning a prize depending on what number came when you rolled a dice. Was it a 1? You won first prize. If it was 2, 3, 4, 5, 6, you didn't win a prize. Maybe you'd like to write a program that simulates that type of randomness. Up until now, up until this morning's lecture, we've not covered the ability to generate random numbers. And so what I'm going to do with you today is show you a couple of functions in Python that allow you to generate random numbers. I'm going to refer to them as random numbers. Technically, they're not random numbers. They're known as, they're strictly speaking, they're pseudo random numbers, pseudo meaning false. They're not truly random because they're produced in a very complicated and predictable way once you've set a seed. And the seed is a number which depends on the current time. So if you ask Python to generate a random number, I'll show you what that looks like in a slide. What it'll do is use a random number generator, a pseudo random number generator that's been initialized with a seed that depends on the current time. And so when you run the program, will influence what random number or sequence of random numbers is generated. And so that really complicated algorithm for producing a number from a seed, the specifics of that algorithm are not important, but it's a complicated function of this initial seed. Because the seed depends on the current time, if you run the program today, tomorrow, next week, in 10 years' time, you'll get different answers because the seed is different, because the current time is different. So let's start with the simplest possible generation of random numbers. We say we're drawing one random numbers. It's simple in two senses. One is, for the next 10 minutes or 15 minutes or so, we're going to be talking about generating one random number at a time. There'll be cases later we'll want to generate many. I'll do them in 20 minutes time. It's simple because we only want to generate one random number at a time. The other way it's simple is that, to start with, we'll build up the complexity. This one's simple because it generates a random integer. It's perfect for simulating the roll of a dice, where we generate a random integer 1, 2, 3, 4, 5, 6, and only those 6 numbers, and we generate them randomly. And we're not interested in generating the number 2.5. That's not a valid throw of a dice. Just 6. 1, 2, 3, 4, 5, 6. They're the only numbers, and we'd like to be able to generate those easily, and we can do that using. Well, I'll show you I'll talk about the code on the screen, then we'll do it live. The first thing is that we need to use an external module called random. So in the same way that we've been importing NumPy and importing matplotlib and importing math, now we're going to introduce the random module. So that gives us access to a number of functions that generate random numbers inside the random module. And so if you look at the code that you can see on the screen here now, we've got A equals 1, B equals 6. They are respectively the lowest and the highest integers that we want to generate random numbers from. So if we specify 1 and 6 as our minimum and maximum, then we generate random numbers as integers in the range 1, 2, 3, 4, 5, 6. And the function that's used to generate those random integers is called randint. And you can see here in the code on the screen, random.randint means that we're using the randint function inside the random module. And then we pass in the parameters A and B, being the minimum and maximum values of the dice. So we could run that code if you want, and there's a hot link there to it. I'm going to do it for you live in Python. So let's go to the console. Let me just take a 1 minute detour. I was slow to realize that the console that comes with my particular PyCharm setup on my computer here in my office, it's different from the setup that's been rolled out in the labs across the campus. What that means is that the console here looks different, or has looked different. It's used some in and out statements that have probably, I know, have confused some of you. Over the weekend, I adjusted the settings on my office computer to use the same console that you're using in the computer labs. So my console here looks slightly different from the one that it did last week, but it now looks like the one that you've got in the computer labs. Okay, so we're at the console. We can import the random module, which allows us to access functions within the random module. We said A is equal to 1. That's going to be our minimum random number. If it was me writing the code, I wouldn't use A and B. I'd use something like ran low and ran high, or something like that, or dice low, dice high, something like that, rather than A and B. They're not very descriptive numbers. Doesn't matter. R1 is equal to random dot rand int, rand int, somewhere between A and B. So we've generated the random number. Let's now print it. 6. Fantastic. Roll the dice. We got a 6. Let's run it again. Print it again. We got a 2. That is the first time in this course we've seen a function which, when you rerun it, produces a different answer. It's random. Generate, roll it again, we get a 1. Run it again, we get a 6. We've already had a 6. That's okay. Roll it again, we get a 3. Roll it again, we get a 2. Now, you'd like to think that if we rolled this dice 1,000 times, 10,000 times, 1,000,000 times, that it would produce the numbers 1, 2, 3, 4, 5, 6 in roughly equal proportion. And that is indeed the case. And there's some nice questions at the end of chapter 2 in the textbook, which give you a chance to validate that. We'll probably roll them into next week's lab sheet, because it's satisfying to be able to generate 1,000,000 random numbers using this rand int function and confirm that they satisfy the properties that we would expect, namely that we get the numbers 1, 2, 3, 4, 5, 6 in roughly equal proportion. And so there you go. We've got the ability now to generate random numbers in the range 1 to 6, should we want. And if you like, we could say A is equal to 10, B is equal to 20, and now generate random numbers in the range 10 to 20. Print R1, we get 19. Generate random number again, we print it, we get 17. Generate it again, we get 16, 14, and so on. So having these upper and lower limits to specify the random integers that we want to draw from, that's really handy. Now, I talked about this seed before. Remember, the seed was the way in which the algorithm embedded in the Python language is generating these random numbers. And the seed's a number which depends on the current time. Sometimes happens when we're debugging programs. It can be really complicating if every time we run the program, we get a different set of data to deal with. because we get a different seed, because we get a different sequence of random numbers. So sometimes when you're debugging programs that involve random numbers, it often helps to be able to fix the seed. And that ensures that an identical sequence of numbers are generated each time the code's run. And that makes the results repeatable. Remember I said before that the 3 steps I talked about when debugging programs, I mentioned that working through tiny problems by hand is a really good strategy. One of the things that relies on is repeatability, so that you know that when you run the program, it's going to replicate the results that you've sketched out on paper. That becomes difficult when you're writing programs that involve random numbers. So it's possible to set the seed or fix the seed in Python. And it basically, all that is a function in the random module called seed, which allows to set the seed to a particular value. Here on this slide, I've chosen it to be equal to 10. And that'll mean that we reset the random numbers to be generated in the same way over and over. What that also means is that if you use the same seed, you could give your code to your friend, they could run it on their computer, and their results would be exactly the same as yours, because the results depend on a sequence of random numbers, and the sequence of random numbers is the same because you use the same seed. So rather than talk about it, let's do it. So here we are at the console. The way that we set the seed is we run inside the random module. There's a function called seed. I'm going to choose, there's nothing significant about the number 10. We'll set it to 10. Seemingly nothing happens. So now let's run our random sequence of integers, and I'm going to generate 3 in a row. And I want you to remember what they are. Let's choose them between 1 and 6 again. Print R1, the first number is 5. Random number, the second one is 1. Third random number is 4. So you notice those numbers there, 5, 1, 4. Let's reset the seed and generate random numbers again. 5, 1. Sorry, I printed A and B. Let me set it again. We've reset. Remember the sequence before was 5, 1, 4. Random number between 1 and 6. Print the random number, it's 5. Random number between 1 and 6. Print the number, it's 1. Random number between 1 and 6. Print the number, it's 4. So by resetting the seed, we've been able to reset the sequence of random numbers that's generated. And that's really handy during debugging. So often a debugging strategy is debug your program with a fixed set of random numbers, and when it's because everything's repeatable, and when everything's working, remove the line, comment out the line that fixes the seed, and rerun the code. So there's nothing special about the number 10. We could seed it with some other different number, generate a random number between 1 and 6, print it, it's 4. Random number between 1 and 6, print it, it's 4 again. So let's reset this, do a third one. Random number between 1 and 6, print it again, and it's 1. So with this funny seed here, we get the sequence of random numbers 4, 4, 1. So let's do that again just to validate that things are working as we expected. Random number between 1 and 6, print, between 1 and 6, print it, it's 4. Between 1 and 6, print it, it's 4. Random number between 1 and 6, print it, and it's 1. So everything's working well. There's nothing special about that random number 10. Sometimes people put their birthday in as a random number seed. There's nothing significant about it. The ability to set your own random seed, though, is really handy. So far, we've got the ability to produce random integers. It's often the case that we want to produce not integers, but real numbers, floating point numbers in a certain range. And there are two functions in the random module allow us to do that. They're called random and uniform. And yes, it's a bit confusing that there's a random function inside the random module, but that's what it is. Random and uniform are actually sort of very closely related to each other. The random function draws a real number from the interval 0 to 1. And the fact that this is a square left parenthesis and a curved right parenthesis means that the number 0 can be generated from that random number process and the number 1 never is, but 0.999999999 is valid. And uniform means we pass two parameters in and we specify the upper and lower limits. So the difference between random and uniform and randint is that random and uniform generate floating point. I should have highlighted that, floating point numbers. So this is an example where maybe we're measuring temperature in a chemical reactor and we want to add some noise onto it to simulate fluctuations in the temperature. Adding a random integer doesn't make much sense, but adding a random number in a range does. Now, most of you will not have done much probability and statistics yet, and that's just fine. We don't need it for this course. But for those of you that have, what we're doing is drawing random numbers from what's called a uniform probability distribution. There's no the uniform meaning they're equally distributed through the range, either 0 to 1 or A to B. So rather than do it, let's do it online. Let's just give myself a fresh console. And what I'm going to do now on the console is pretty much replicate what's on slide 14 in the printed slides. So we import from the random module, library if you like. X equals random. A couple of interesting things about this line here that I'm going to highlight in blue. One is that random looks a bit strange. That's the random function inside the random module. So we use the dot to separate the two. It's like having a file inside a directory. Random module, random function inside it. The other one is even the random function generates a number between 0 and 1, equally distributed through that range. Even though no parameters are passed in, it's still necessary to use the empty parentheses here. So if we generate X in this way and print the value of X, now we get a random number that's chosen in the range 0 to 1. Generate another one, print it, we get a number also in the range 0 to 1. So I'm just drawing successive values and printing them. Let me do it in this way. So I can just do one up arrow. I'm going to generate a sequence of random numbers, one after the other. And you can see they're all in the range 0 to 1. They're never less than 0. They're never greater than 1. And so the random number generator in Python behind the scenes is taking a seed and generating random numbers in that range. The other way we can generate the uniform function is also within the random module. And this allows us to generate random numbers in the range 10 to 20, for example. A floating point number, not an integer, in the range 0 to 20. Let's print Y. There it is, 16.93. So let's just do this. Rather than assign it to the variable Y, let's just print a random number and I can just up arrow and see these numbers are all falling in the range 10 to 20. One call after another, different random number being generated. And of course, you can use the seed function to reset, and it also affects these random numbers that you see here. Good. Okay, we're almost done. I told you today's lecture was going to be a bit shorter than the others. That's to give you a bit of headspace to keep yourself focused for the assessed lab. So far, we've used the three functions, randint, random, and uniform, to be able to generate one random number at a time. Randint generates an integer, uniform and random. Random and uniform generate random numbers in a real numbers, floating point numbers in a range. But they only generate one at a time. And you saw me doing that by generating them at the console and then generating them with an up arrow just one at a time. And that's really convenient. Sometimes when I generate small numbers of random numbers, that's a great way to do it one at a time. If we want to generate an array of random numbers, we could create an empty array and then fill it one random number at a time using calls to any of those three random number generators, and that would be fine. It would work, but it wouldn't necessarily be fast. There's a faster solution, and that's to use random number support that comes from the NumPy library, and it's also called. It's also got a module called random. So I'll talk about what's going on this slide, and then we'll do some examples live. Let's look at the code here. First line, this is done at the console, and that explains this in one, in two, out two, and so on. I'm now avoiding the use of that particular console because it's not the one that's used in the labs. So our first line is to import NumPy as NP. That's now becoming a common line for us. Remember what that does is means it gives us access to the NumPy library, and it gives us the NP abbreviation, so we don't have to type out NumPy all the time. And let's look at line indicated by in2, np.random.randint164. Let's unpack what that means. np.random.randint means it's the randint function inside the random module inside the NumPy library. So it's sort of like a hierarchy that's going on here. So in order to access the function that we want, randint, which is going to generate random integers, in order to access the function, we need to access the module, and the module sits inside the NumPy library. So we import the NumPy library, and then we just use np.random.randint to access this randint function. Now, the randint function itself has three parameters, 1, 6, and 4 in this case. That means draw random numbers between 1 and 6, but not including 6. So this will actually generate random numbers between 1 and 5. It's confusing indexing again, but we live with it. And it'll generate 4 of them. But this time, we can, but this time we're generating 4 integers, not just 1, but 4. So let's do that live. I'll literally type in get myself a fresh console. Import NumPy as NP. Excellent. np.random, so that means the NumPy library, the random module in it, and the randint function inside it. This will generate 1 random integer in the range 1, but not including 6, and this will generate 4 of them. So these 2 lines are exactly in the printed lecture slides. Notice that what's returned is an array, not just 1 random number, but 4 of them. We want to generate 40 of them. Boom, There they are, 4 random numbers. And notice in the random numbers, see that the number 6 never occurs. That's because they're generated in the range 1 up to, but not including 6. In other words, 1 to 5. If we want to generate 400 of them, no problems. Boom, there's 400 random numbers. Want to generate 4,000 of them, no problems. Boom. It won't print them now, but let me print that for you. Oh, and it'll produce the first few and the last few, but it's actually generated an array of 4,000 elements. Let's check that. If you don't take my word for it, let's ask for the length of that array, and it's 4,000. So even though it's only displayed the first 3 and the last 3 numbers, the rest are indicated with dots, it has actually generated 4,000 random numbers for us. And if we want to generate 40,000, we can do it. No problems. It took a little bit of a blink there, but it's very powerful, and that's much faster than calling the random module 40,000 times. Okay, we're almost there. Let's go back to the our slide. Okay, the last 2 functions are again random and uniform. Notice there's a pattern going on here that the NumPy library is using the same function names as randint and random and uniform. It's using the same names as it was in the random module that was built into Python. That's deliberate. That's deliberate to avoid programmers having to memorize different names for the same functionality in different places. But it also means we need to be particularly careful about our import statements so that we know where we're getting our random numbers from. In this case, it's really clear. np.random.random generates 4 random numbers, 4 floating point numbers in the range 0 to 1, returning them in an array, but it's calling it from inside the NumPy library. And the final call, np.random.uniform 1024, generates 4 floating point numbers, 4 floats, in the range 10 to 20, but not including 10 to 20. So let's do that just for fun, just to verify that the functionality is there. np dot presentation mode so you can read it. Excuse me. np.random.random4. Again, the random function inside the random module inside the NumPy library. And the 4 means that we're going to generate 4 random numbers in the range 0 to 1. That's what the random function does. And there it is, returned as an array. We've got 4 random numbers in the range 0 to 1. And they're uniformly spaced, rather uniformly distributed, meaning that any random number, any floating point in that range 0 to 1 is equally likely. There are other distributions that arise in engineering and that we may or may not need in this course. We'll see how we go, but at the moment, uniform distribution is very powerful. Generated, we run it again, we get different sequence of numbers, run it again, a different array of numbers. The final was, so the random function is a little bit limited in that it always chooses numbers between 0 and 1. But depending on our application, we might not want that. We might want a more general choice. So in this case, let's choose numbers in the range from 10 to 20, floating point numbers in the range 10 to 20, and 4 of them. So now you can see they're all in the range 10 to 20, and there are 4 of them. Let's generate 40 of them. There they are in an array displayed for us. None of them are less than 10. None of them are more than 20. And all of them are sort of equally distributed through the not equally distributed, but had drawn from a uniform distribution. It's also possible to, let's just generate, we can also fix the seed inside NumPy. So we can set the seed to 10 again, for example, and then generate 4 uniformly distributed random numbers between 0 and 1. There they are. Let's reset the seed to 10, generate them again. What's going to happen when I generate those random numbers? What's going to happen? They're random. They're random, but I generated them with the same seed. So in fact, they will be the same random numbers as were generated previously. This set is the same as this set because I reset the seed. If I run it again, I'll get a different set. But if I reset the seed to 10, generate those 4 random numbers, I get those random numbers back again. Might seem a bit funny that I'm focusing on generating repeatable sets of random numbers when the whole point of randomness is to be non-repeatable, but for debugging, it's super useful. And that takes us to the end of today's lecture. So super quick summary. We looked for the last time, we did some revision on for versus while, similarities, differences, when you might choose one over the other. They're both useful, and I'm not going to preference one over the other. Sometimes I'll ask you to use one particular structure just for the sake of consistency, but they're both useful. While loop usually takes a little bit more to set up because you've got to initialize and then increment within the loop body, but they're also very flexible and often very efficient for solving particular types of problems. We then discussed some debugging strategies, and again, not for memorizing, but for just starting to change your mindset a little bit rather than my program doesn't work, what's going on. Maybe something like my program doesn't work, the first 2 iterations work correctly, then I don't understand the 3rd iteration. 3 different strategies there. You could write a book on this stuff, and people have, but just to get you started, don't feel bad that your programs aren't running exactly as you wanted them first time. That's what programming often does, especially when you're learning a new language. And the final one was random numbers, both the ones that are built into Python or available through the standard random module, but also the ones in the NumPy library. And again, I would preference the ones in the NumPy library over the random module, simply because the random functions inside the NumPy library have been written in such a way that they're built for speed. Ease of use too, but behind the scenes, it's much faster to generate random numbers using the NumPy library than it is one call at a time to the sort of the standard random module. Nothing wrong with the standard random module, but NumPy library has been built from the ground up for solving numerical problems. And let's face it, we're here as engineers learning how to use the Python language to solve engineering problems. And so computation is at the core of those, and efficiency is part of that. Wonderful. So 10:30, so right on the 90 minutes, which is great. Good luck to each of you in your assessed labs this week. There'll be a little bit of traffic on Discord, and also some announcements on Blackboard as to how those assessed labs will work. But you can expect to do an hour's worth of problem solving, sample problems that were presented via Blackboard and on Thursday's lecture. And the idea is that you demonstrate them to the demonstrator on the spot, and you and the demonstrator, the session finishes, and you know what your mark is. It'll appear in Blackboard within a couple of days, but you'll know your mark when you leave the session. It's not like the demonstrator goes back and marks in their office. The class is too large to do that. It's an on-the-spot assessment. Wonderful. Thanks so much for your company. I'll catch up with you again, if not earlier than on Thursday's lecture. Until then, bye for now.